audiovisual company that provided all the equipment that made this possible. I think we're ready to start, actually. So yeah, David, off you go.
Very good. There's one more test that I would like to make, since so far I heard neither Edgar nor José speak. Can we make sure that they?
Okay. Can you hear me?
Yes. You're loud and clear. And Edgar, you too?
Hello. 1, 2, 1, 2.
Hi. Yeah. Okay. Perfect. That does seem to have done the trick. All right. Perfect. Should we maybe wait? I can see some people are still coming in and sitting down. Maybe let's wait just one more minute and then we'll get started. Okay. I hope everybody still hears me well. It is my great pleasure to chair the Summer School in Astronomy Roundtable in General Relativity. Do you hear me?
Yes.
Yeah. Okay. Perfect. So let me start by introducing the panel members. So sitting on the left in EA4, we have Dr. Edgar Gasperin. He is an invited professor at IST, and he holds the competitive FCT investigator grant. Edgar works in mathematical relativity, and in particular, he's a specialist in the structure of space-time at infinity. Next up, we have another local. That's Professor José Natário, who is a professor in mathematics here at IST. He has worked on a huge range of topics in mathematical relativity, such as rockets and warp drives and cosmic censorship and wave equations in curved spacetime. And he's also very active in outreach, which gives rise to one of my favorite false friends from Portuguese to English, namely divulgation, which we usually call outreach, but when Portuguese people translate it, they call it divulgation. And so, well, what I recommend everybody in the audience to do is go and check out his articles. They're available on his website, on his webpage, many of his outreach articles. Next up, we have Professor Bob Wald, who is a professor at the University of Chicago. He works on a range of topics in classical gravity and also related quantum phenomena, and he's made major contributions to both. He's also very well known as the author of the go-to book on general relativity, and so a personal anecdote there is that when I moved from the UK to Germany, I took one book and one book only with me, and it was not a religious text. So that gives you a sense of how important that book is to people working in the field of gravitation. Last up is Professor Margaret Geller, who's based at Harvard and Smithsonian. She's an astrophysicist who works in cosmology and extragalactic astronomy, and she's well known for creating pioneering maps of the nearby universe. And I checked her webpage in the run-up to this, and I see that she's given a huge number of public outreach talks, something like 200. That's incredible. So I'd like to extend a warm welcome to all of you. Thanks so much for being here. The way that I'd like to run the event is now to ask each of you in turn to give a brief introduction, 5, maybe 10 minutes, telling us who you are and what you work on and what excites you in science. So I'd like to go through the panel members in the same order that I just introduced you. So let's start with Edgar.
Okay. Hello, everybody. My name is Edgar Gasperin. I'm an early career scientist here at Técnico. I have a grant given by the main Portuguese funding agency, let me just briefly say what is my trajectory. So I did my undergrad in Mexico, then my PhD in the UK. Then I moved here to do a first postdoc. Then I moved to France to do another postdoc. And now here I have this starting career grant. And well, the type of research that I do here, so I do something that is something in between physics and mathematics. So the topics that I kind of developed during the PhD and during the postdocs and now they have evolved around the idea of the notion of infinity. So in GR and in many other areas of physics and mathematics, the concept of infinity has gotten the attention of not only the mathematicians, but also like even philosophers. So everything that I do is sort of related to this concept of infinity as understood in general relativity. That's all.
Next up, José.
Okay, I guess it's me now.
Yes.
So my name is José Natário. I'm a professor of mathematics here at Instituto Superior Técnico. In fact, I've been teaching some of the organizers this year. I taught them a course in calculus, and I can tell you they were really good. They were like one of the best courses I've ever had here. So I am a mathematician, so my training is in mathematics. I did a mathematics degree. Then I went to the UK to do my PhD in mathematical physics, and then I came back. The sort of mathematics is very wide, so you'll find mathematicians doing all sorts of different things. So some of them are very pure. They do research in things like number theory, or even more abstract areas that you've never heard of, probably. And then you have more applied mathematicians that are interested in applying mathematics to either understanding nature or real-life problems. And I'm one of these later kinds. So my interests are in the mathematics behind the general theory of relativity. Of course, you're still young. You don't know much about mathematics, but you'll find that in mathematics, the way in which people predict what's going to happen in a certain phenomenon is by using something called differential equations. Maybe you've heard of it. And the equations of general relativity are just very complicated, nonlinear differential equations. And so many mathematicians, myself included, basically study these equations and their consequences. There are a number of problems that we study. One of them I can tell you right now has a sexy name. It's called the cosmic censorship conjecture. And so that's one of the things I've been studying over the years. Thank you.
Thank you, José. Bob, would you like to take a few minutes to introduce yourself?
Yeah, so I'm Bob Wald. I got my PhD degree at Princeton 50 years ago, where I overlapped with Margaret Geller. Was a postdoc at Maryland for 2 years, and I've been at the University of Chicago now for the last 48 years or so. My work has been, I'd say the majority or 2/3 has been in classical general relativity, and most of the remaining 1/3 has been in quantum field theory and curved space-time. I mean, developing the theory of quantum fields, but in a classical, gravity isn't quantized in this framework. I mean, it's not intended to be an exact theory of nature, but a good approximation for what's going on near black holes and so on, with Hawking effect and so on. That's what I've devoted the vast majority of my research efforts to, and probably half of the work, I mean, much of the work in quantum fields and curved space-time, and a lot in classical general relativity has been devoted to the theory of black holes, and most particularly the relationship between black holes and thermodynamics, this remarkable fact that black holes obey thermodynamic laws, and with the Hawking effect, they even radiate like thermal bodies. So that's, in a nutshell, the kinds of things I've been working on and doing the last 50 years or so.
Fascinating, thank you. Next up, we have Professor Margaret Geller. Margaret, would you like to take a few minutes to introduce yourself?
Yes, I mean, I was an undergraduate at the University of California, Berkeley, in the famous 60s. And I overlapped in graduate school with Bob, as he said. And it's really amazing that we're both on this panel, and it's wonderful to see one another. And since then, I've been at the Center for Astrophysics, except for a year and a half at the Institute for Astronomy in Cambridge. When you ask what I do, what I would say is I make maps. And what do I make maps of? The way galaxies are distributed on very large scales in the universe. In the mid-1980s, I made pioneering maps of the nearby universe, and those maps showed what is now known as the cosmic web, the characteristic structure that galaxies delineate throughout the universe. These patterns are the largest we know in nature, and they extend for hundreds of millions of light years. Since then, I've worked as technology has improved, this field has grown enormously, and I've worked to extend these maps into the more distant universe. The universe, of course, acts like a time machine. So as we look out in space, we look back in time. So the entire record of the way this amazing pattern evolved is there for us to observe. Not only that, but underlining this issue is a mystery. Actually, well, there are many mysteries, but one of them is that 85% of matter in the universe is dark. And we have still no clue what it is, even though it was first discovered almost 90 years ago. We do know a lot about where the matter is. And one of the things I do is to try to use the patterns in the galaxies that we see compared with what we call gravitational lensing, which is a consequence which is predicted by general relativity, to relate the distribution of matter, the total matter, to the light emitting matter we can see. And this is one of the big efforts in astronomy today as we take advantage of the amazing evolving technology that we have.
Thank you. That was a perfect summary, and very nicely, it actually dovetails beautifully with the questions which the students had prepared for us. I don't know if that was by design or not, but well done. So the next part of the roundtable, and the next part, what I'd like to do is to pose to members of the panel a kind of curated list of questions which the attendees of the school have collected. And so let's start with Margaret, so as not to break our nice flow now. I suppose maybe here the first question, you just mentioned in your introduction that we've known that dark matter was there for 90 years already, or almost 90 years. Could you explain a bit about, well, how do we know that it exists? What's sort of the development of that in those 90 years?
Okay, I'll do that. Can I'll share my screen.
Yeah, you can share screen. Also, we can see that your share screen is working because we've got a camera aimed aimed at the lecture room.
So, can you see my slide?
Now I do, yes. I think they can, because I can see that they can.
Okay. So in 1933, a rather wild character named Fritz Zwicky, who was working at Caltech, first discovered dark matter in the universe. The picture shows what a character he was. He did it by studying this object. So this is an image of the Coma cluster of galaxies, and it's called that because it's in the constellation Coma Berenices. It's the most massive nearby cluster of galaxies that we know. Every fuzzy object you see here, and they're all sort of orangey, is a galaxy. And the most massive ones, these guys, are among the most massive kinds of galaxies in the universe. They're 10 times the mass of the Milky Way. Zwicky had the amazing insight to try to measure the mass of the cluster. And he did that by measuring how these galaxies move relative to one another. Then he assumed they formed a bound system, and he used those velocities, applied Newton's laws to measure the mass of the cluster. He calculated the mass first by adding up the stars, or he figured out how much mass there had to be in stars to account for the light he observed. Then he calculated the mass from Newtonian gravity, and the mass was an order of magnitude more than what he calculated to account for the stars. This was the first study of what was called missing mass, and later became dark matter. As time went on, people recognized, Vera Rubin in particular, recognized that by measuring the motions of stars in nearby galaxies, she figured out that every galaxy, like our own Milky Way, lives in a halo of dark material. Since then, we have other kinds of methods for figuring out how much material there is, and there are many. And one of them relevant to this symposium is gravitational lensing. Amazingly, Zwicky was the first person also to recognize that gravitational lensing would provide the clue to the masses of systems of galaxies. So in 1937, he suggested that. It wasn't until the 1970s that people first detected gravitational lenses in the universe. And certainly today, we can see, and I'll stop now because that's another question, how we actually do it. But certainly today, gravitational lensing in all its guises is used to measure the masses of galaxies, the masses of clusters of galaxies, the way matter is distributed in the universe.
So when you said then that he, in doing this calculation, he got an order of magnitude difference, how has that number now changed? Because it sounds like it's a sort of, then the number was like 10%, and if I remember well, it's
still not very different actually. And what's amazing to me, this is an amazing thing about science, I think. And I don't know whether Bob and others would agree with me, but it's amazing how a little bit of data can tell you a lot if you make a judicious choice. So he measured what we call redshifts, and I can explain how that works later if you ask. I have a little movie, but he measured redshifts for something like a dozen galaxies in the Coma cluster. Today we have 1,000, and we get the same number. Now, of course, we get it more accurately, but it just shows you how, science is about explaining a lot with a little.
Yes. You maybe following up on that kind of how things improve as we get more data. Then recently there's a new space telescope, JWST.
Yes, it's an amazing.
It's truly right, and I suppose that fits exactly with this question of having more data. How is it going to help compared to what went before?
Well, I mean, it depends. That's a very broad question. So I think
you can interpret it as you wish.
Yeah, I mean, I have a sort of sequence of slides about lensing and how it works, and I don't know whether you want me to go through those, ending up with JWST, or you want to give somebody else some time to talk about it.
I'm happy for you to continue, since I think it makes sense to kind of tell one story and then and then move on to the next.
Well, then we'll do that. So you all know that in 1915, Einstein developed the theory of general relativity, and the others on the panel know a lot more, use general relativity more than I do. I only use the results, and here is Einstein surfing on the gravitational waves. So the basic idea of general relativity is that matter perturbs the geometry of space, and as John Wheeler used to say, the geometry of space tells matter how to move and also tells light how to move. So here's a graphic that shows how matter puts a dip in space-time and it bends the path of light. And this is what produces the phenomenon that we call gravitational lensing. If you have an object, a bright object, say a point source behind a galaxy, so here on the left, you see a galaxy, which is a few billion light years from us. And you can also see a faint ring, which is the gravitationally lensed image of an object, which is 10 billion light years away. If you process the image and subtract the galaxy, you can see the ring. And of course, we can tell by measuring this redshift that I mentioned before, we can tell exactly what the redshift of the galaxy is, and the ring, the size of the ring tells us something about, then tells us the mass of the galaxy. We can also measure the mass of the galaxy by measuring the motions of stars inside the galaxy, and we can compare the two, and we find, surprise, surprise, that galaxies have dark matter in them. Now, gravitational lensing can be very complicated because, and this is leading up to the most amazing JWST image, which many of you have probably seen, but the most massive bound objects in the universe is a video of the way the cluster distorts background objects. So in this image, the red is the projected matter density of the cluster. So it has a center here and it has a little bit that's attached over here. And each of these blue points represents a background galaxy. And as you see near the cluster, they're distorted, and they're distorted because the light coming from these objects is bent by the fact that the matter in the cluster distorts space-time around it. So what's going to happen as I play the movie is that the background will move past the foreground cluster. So let me do that, and you'll see how the shapes change. So you can see that objects that get close to the cluster are distorted a lot, and we call that strong lensing. And it always looks like parts of rings, but they're not exact rings, because the objects aren't right behind the center. And not only that, this cluster isn't exactly symmetric. Then you can see out here, everything is distorted just a little, that there's a net tangential distortion, and that's what we call weak lensing. Strong lensing is easily observed. Weak lensing you can't see with your naked eye, but if you have deep images, you can use the hundreds of thousands or millions of galaxies in those images to collect up these tiny distortions and measure the masses of the foreground objects. So here's an example from my own work of what happens when you first observe the galaxies and then you observe this weak lensing signal to measure the mass distribution. So on the left is the density of light. So more or less what Zwicky saw in the coma cluster. So the red peaks that you see here are peaks in a complicated cluster of galaxies, more distant than the coma cluster, much more distant. The coma cluster is 300 million light years from us. This is 5 billion. So the light that made this image originally traveled for 5 billion years, didn't hit any. Here you can see some wimpier clusters. So now what we did was take a very deep image with the amazing Subaru telescope on Mauna Kea in Hawaii. This is an 8-meter telescope, and it right now has the world's largest camera mounted on it. It is a gigapixel camera, and it images 1.5 square degrees of the sky at a time. So for calibration, the moon covers 1/4 of a square degree. So what we do is we measure the distortions of millions of very faint galaxies that are 10, not 5 billion, but 10 billion light years away. And we make a map of the matter distribution that distorts their light. And here it is. Now you can see it's pretty noisy, but you can see the same clusters here. And by doing this, we can figure out, and you can see a cluster here and so on. And that's how we figure out how much dark material there is relative to light emitting material. Now, some clusters of galaxies they have the right thing in the right position behind them. So they act as strong lenses and they make these beautiful arcs, just as the video suggested. So this is a distant cluster of galaxies, again, 4 or 5 billion light years away. And these lensed arcs are galaxies that are 10 billion light years away. So this is an image from Hubble Space Telescope. So Hubble Space Telescope is an optical telescope. It's a 2.5-meter telescope. JWST is a 6-meter telescope operating in the infrared. And the reason it operates in the infrared is that we live in a dynamic, expanding universe. And as the space of the universe stretches, so does the wavelength of the light that propagates through it. So when we see distant objects, their light is shifted to longer and longer, redder and redder wavelengths. So if we want to observe the high redshift young universe, we need to observe in the infrared. So here is the deepest image ever taken of the universe, taken by JWST. I might mention that my wonderful colleague, John Mather, who's a Nobel laureate and also has been a friend since I was an undergraduate, has been the chief scientist for JWST, and the success of JWST has a lot to do with him. Now, what do you see here? This is an infrared image. So the wavelengths are microns. So it's between sort of 0.7 of a micron and 5 microns. And the whitish fuzzy objects are the galaxies in the cluster. And the cluster is called SMAC something or other. It has a telephone number. And these fuzzy objects are the galaxies in the cluster. And again, the cluster is about 5 billion light years away. And you can see the orange guys are all the distant objects, which are 10 billion light years away or even more, that are gravitationally lensed by the cluster. And here, because of the exquisite optics of JWST, you can even see the shape of this weirdly distorted galaxy, which is lensed by this cluster. So by using these arcs, you can actually, and by knowing how far away they are, you can make a detailed model of the way matter is distributed in the foreground cluster. And this is one of the most accurate ways to measure the matter distribution in a cluster.
So can I ask a question there? I'm curious. So is it the case here that the model already exists, and then now JWST gives data, and then the numbers in the model are being fitted?
Oh no, you have to. I mean, you know how light propagates. You know how light propagates. So what you have to do is you have to figure out which. So there are a variety of ways that it's done, but one way that it's done is we have a problem because you have the galaxies in the cluster, and then these galaxies are embedded in an extensive dark matter halo. So you know how light propagates in the universe. So you have to model the material associated with the galaxies and the halo. The halo, we know sort of a mathematical model for what the structure should be, and we fit the parameters to the data.
Okay, and it's JWST that then gives those numbers.
But then you have to also fit the component for the light, and to do that, you use the data. So what you do is some models, not all, suggest that the light traces the mass. So for the galaxy component, you figure out which of these are actually members of the cluster, because of course you look through it. So lots of the galaxies here have nothing to do with this cluster. They're either in front of it or back. And then you make a model for those as well. And you have a whole bunch of redshifts or distances. I'll show you that in a minute for these arcs. And you know the redshift of the cluster, and you know how the material bends the light, so you can make a model for the projected matter distribution. So here is a close-up of the center of this cluster, and you can see this wacko thing that's actually a galaxy. And you can see all these arcs. One of the weird things about all this is that the light paths around a complex object like this are so complicated that many of these arcs can be an image of the same galaxy. And JWST not only makes the images, but it also spreads the light out into its colors and takes what we call a spectrum. So here you can see the same image. So here's that central galaxy, and here are two arcs, and you'd like to know, are they the same galaxy or not? On the right is the spectrum, and we can identify features in the spectrum with the atoms or ions that are responsible for light at that wavelength. And you can see the spectrum for these two arcs is identical. So these are the same galaxy imaged by this path that's sort of jerked around by the projected matter distribution cluster. And it's by measuring the redshifts or the distances to these objects that we can make a model for the matter distribution.
Were there examples of this known before JWST?
Yes, so there are, as you saw, the previous, so here is an example from HST, Hubble Space Telescope. So these are optical images. And with the Keck telescope, which is a 10-meter telescope on Mauna Kea, people managed to measure redshifts, especially of these blue objects, from the ground. And so a number of these have been done from the ground before, but the thing about JWST is that it reaches deeper. So some of these galaxies that are imaged, it also not only does it distort them, but it magnifies them. So some of these galaxies are among the youngest galaxies we know in the universe. So this is one of the ways in which JWST challenges what we know about how structure forms in the universe. So some of these little faint objects here are galaxies that are present only a few 100 million years after the Big Bang. So that's very early relative to what theory suggests, and people are trying to understand exactly what that means. So gravitational lensing not only enables us to measure the mass of these clusters, it also enables us to look at objects that we would never see in any other way that are at very high. We can talk about the redshift or the age of the universe. So the redshift is 20, whereas the redshift of this cluster is a half. And you can ask, how old is the universe? The universe is only a few 100 million years old at a redshift of 20.
So something that I'm curious about hearing all of this is sort of in the context of gravitational wave astronomy, which we'll come on to a little bit. There's a clear sense that, you know, if I've got a ground-based detector, then it's good for a certain type of thing. And when we eventually have space-based detectors, like how LISA is going to be, then that will be good for a different type of thing. But in this case, is it fair to say that JWST just sort of smokes all of the competition now? It's like it's going to be the only game in town, or is there still of that kind of complementarity?
It depends on what you want to do. I mean, unfortunately, there are many challenges to ground-based or another. So those two things together may kill ground-based observing, but science is not going to kill it, because you can build a bigger telescope on the ground than you can have in space.
Sure.
And so the whole idea is to have a light bucket and collect the light. So if you want to spread the light out into its colors, as happens here for faint objects, then things on the ground win because they're bigger. In the optical, not in the infrared, because we have an atmosphere. But in the optical, you win on the ground. So there are many things that you would still do on the ground, provided they're not clobbered by climate change and satellites.
Okay, so that all of the ground-based telescopes, they can breathe a sigh of relief. I remember maybe just a couple more on JWST. I remember in the run-up to the launch, there was sort of a lot of controversy about the cost overrun. Like it was a factor of 20 or something, right? Do you think that now that the images have started coming in, that's kind of convinced the naysayers now, and that people have sort of now they accept, okay, this was the right experiment to do?
Well, I mean, I think people are very impressed by the results, and I think it's a testament to the people who built it. And I think,
yeah, for sure,
you know, there's a tendency to lowball these things and not know how much they're going to cost. I mean, so I think, you know, the results are certainly going to be impressive.
Right, and is it expected? So in the case of Hubble, right? Hubble still, I think, is going strong, right? Is it expected?
Hubble is still operating. Yes.
So is it expected?
It complements JWST because the Hubble is an optical telescope, and there will be ostensibly other things, but I mean, Europeans have a mission which is called Euclid, but it needs to be launched on a Russian rocket, and you can imagine what the likelihood that will be launched.
Yeah, right now 0.
Right.
I see. So, but my question was going to be then, in the case of JWST, is it expected also to have a similar sort of 20, 30-year lifespan?
No, because no way. No, because JWST, there are two things about JWST. One is that it's located at the second Lagrange point, which is a saddle. And that's not stable. So JWST, so the way it works is JWST orbits the sun with the Earth. So if you look at the Earth from the sun, JWST is 1 million miles farther away from the sun than the Earth. And they orbit around together. But JWST has to have little propellers to keep it at this Lagrange point. If it didn't, it would float away, right? Because it's not a minimum, it's a saddle point in the potential. And furthermore, it's an infrared telescope, so it needs to be cooled. And coolant goes away. So the longest wavelengths will not operate much longer than the prospective lifetime, which I think is 5 years, and the shorter wavelengths might operate for 10, but it's not like Hubble.
So it's interesting. Hubble will probably
it has a finite. There's no question that it has a finite lifetime, and then of course there are other issues like what hits it and so on, because there's more and more junk in space.
So maybe
hopefully it won't have any catastrophic accident, but it does have to, unlike HST, which is in an orbit, right, and doesn't have to be pushed around, and also it doesn't have to be, it's not cooled. JWST is finite for those two reasons.
So maybe changing tack slightly then, in your field, then what would you say have been the most important developments on the theoretical side recently, or do you think that sort of everything now is data driven?
Well, I mean, on the theoretical side, there are big unanswered questions. One is, well, it has to be answered, I guess, in the laboratory. What in the world is the dark matter, and what in the world is the dark energy?
Yeah.
On the theoretical side, I mean, a lot of what people do is driven by very large n-body simulations. And one of the leaders in that is Volker Springel in Germany, and he has a suite of simulations called Illustris that people use to try to understand or try to interpret the observations. And so there's a strong interchange between these models and the observations, because of course, we can't do an experiment, we only observe.
Yeah, so those type of simulations, they somehow straddle the gap between observations and theory somehow.
Yes, I mean, there's a basic theoretical model, and then you have the parameters of the universe, which you put in, and then the simulations enable you to make detailed tests of the underlying model. And these simulations have been more and more fancy and have been more and more successful, but they also contain a lot of parameters that are hard to test.
Well, thank you so much. All of that was very fascinating. I wonder if any of the other panelists want to come in with any questions, comments, queries. And
I don't really have anything to add beyond, it was fascinating to listen to that. And I don't have anything to add beyond what Margaret said, which was fascinating to listen to.
Yeah, it was, I think, spellbinding. In that case, let's maybe move on. Margaret, could you stop sharing there?
Yeah, sure.
So then I'll have a more than microscopic view of the of the lecture theatre. I wanted to move on next to Edgar and José. And well, actually, it's interesting. Before we started, Bob and Margaret were having just amongst themselves a discussion of kind of the the type of problems that people get attracted to. And I think, Margaret, it was you that was saying that somehow it's like your inner muse draws you to, or maybe your character sort of draws you to certain type of problem. And so my question for Edgar and José, the more sort of pure mathematicians here, the question is, what do you think separates how physicists and mathematicians approach problems in physics? And don't fight with each other too much.
First of all, I wouldn't split people into physicists and mathematicians. It's much more like a spectrum. So it's like light. You have blue light, and then yellow light, and then red light, and it's the same. You have the pure mathematicians, which would be at one end of the spectrum, and they are studying number theory and algebraic topology and whatnot. And then you have people who are more interested in applications or in physics, let's say, and I mean, most of the people that I know that I work with, I don't think of them as pure mathematicians or pure physicists. They're a mix. And I mean, a good example is Professor Wald. When I was doing my PhD in Oxford, the textbook, I mean, he is a physicist. He works in the physics department. But the textbook that everybody used in the mathematics department was his book. But having said that, of course, there are some differences in the way people think about problems. I think the difference that is most obvious is that mathematicians tend to be more worried about details and that everything fits together correctly. Whereas, I mean, and of course, people sometimes fight a lot. The typical fight between a physicist and a mathematician is that the physicist says the mathematician is wasting time, and of course that the thing he's trying to prove it's obviously true, and he should move on to more interesting stuff. And of course, the mathematician thinks the physicist is not rigorous, and everything he does is like building a castle of cards and so on. But I mean, that's the sort of cartoon difference that people often
do either you or Edgar know a kind of a killer example in sort of in favor of the mathematicians there, like in favor of that? So the question is, do you know a case in which the physicists sort of did the calculation in the physics way, and it seemed like it was perfectly correct, but then later they turned out to be completely wrong because of a detail in the mathematics? Do you know an example like that?
Well, I can say an example, partial example that actually connects with the actual research of the moderator, which is like, so one thing that you want to do in physics and maths is like to solve numerically these partial differential equations, which are very difficult. And the story that I've heard from the numerics people is that at the beginning, their codes in numerical relativity, they were crashing and they were failing. And it was because of a mathematical subtlety about PDEs, about the difference between something that is called weakly hyperbolic and strongly hyperbolic. So actually the codes were crashing, and it was because of this mathematical subtlety. And it was until the analysts and the mathematicians came into the game to sort of analyze this issue, it was that was able for the numerical codes to actually be successful. So here you can see where an example of this cross-feeding interaction, where more applied side, let's say the numerical part, benefited from the purely analyst side. And I think there might be examples where the analytic side learns from the physics side.
Yeah, that's really, that you're right, Edgar. That's a great example, and it's such a if the people working on the code had have been forced to sit in a room with Yvonne Schocke-Bruhar in the 1970s, and she'd have just told them what to do, maybe the binary black hole problem. So that's the problem of calculating the evolution of two black holes. Maybe that would have been solved, much sooner. Margaret, you wanted to come in there.
Yes, I wanted to say just a brief word about one of the most famous examples, I think, where the theorist was wrong. So when Einstein developed the theory of general relativity and he first wrote down the cosmological solution, he discovered that it predicted a dynamic expanding universe. And he didn't like that, so he added the cosmological constant to stop it. Then along came Hubble. Guess what? The observations showed that we live in an expanding universe. So that is probably one of the most famous.
That's
example. So I think one of the important differences between, in physics, you can't prove anything. In mathematics, physics is a consistency argument. Mathematics, you can prove things. And physics depends on having experiment that tests the theory. So I think that is, to me, those are the most important differences. But anyway, I think that historical example is an amazing one.
Yeah,
Thanks.
I quite agree. Thank you. So
well, in defense of Einstein, the cosmological constants turned out to exist. But I agree with Margaret that, of course, at the time, Einstein was just, I mean, it's very weird because there were already experimental evidences of redshifts in the nearby galaxies, but he seemed to be
but the ones very nearby, the ones very nearby are coming toward us.
Right. But I think they knew about 20 redshifts and like 5 were.
Yeah, there weren't. No. It took a while. No, because all the nearby galaxies are coming toward us because they're all bound to us. And so you had to get to bigger enough distance to see the expansion. But I should also mention that the cosmological constant we have now accelerates this expansion, not decelerates it. So it's the opposite direction from Einstein.
Yes, but what's amazing is that Einstein was building these cosmological models, but he was paying very little attention to data. And if he had, as you said, he probably could have come up with the expanding universe. He could have predicted it, maybe.
No, I don't think so, but because the data didn't exist till
maybe. You're saying the data didn't exist until much later.
That's correct. So it took a distance measure, which Henrietta Leavitt developed. It took quite a while, actually.
Jose, I had a follow up which I wanted to ask you, and this is sort of I guess I'm asking you because of your Oxford background, and the question is this: so together with Gensel and Gates, for quite different work in 2020, Penrose was given the Nobel Prize for his work on singularity theorems, and I wondered if you could explain to everybody what they are.
Yes. Well, that's the so Penrose, by the way, he's a mathematician. Is a good example of someone in the spectrum between a mathematician and a physicist. So he actually, his PhD was in mathematics, in algebraic geometry, actually, but he started getting interested in physics. And his research was then mostly in physics, in general relativity. And general relativity is good for mathematicians because you have a very well-defined model, mathematical model, that you can study mathematically. And that so the Penrose singularity theorem, which was sort of a huge breakthrough at the time. So it was like it came out of nowhere, basically. So it was something completely new. So I think he proved it around 60-something, 65 maybe. So this theorem tells you that under certain circumstances, you have singularities in your theory. So first of all, what is a singularity? I cannot tell you that exactly, but think of it as it's essentially a point where the gravitational field becomes infinite. That's sort of the idea of a singularity. I'm not being completely honest, but it's a good enough idea. So at the time, people knew that people had this spherically symmetric model of black hole formation. So they knew an example of a solution of the theory where a homogeneous sphere collapses and turns into a black hole. And they knew that in this one example, there was a singularity. However, this model was really simple, was spherically symmetric. And of course, if you have something spherically symmetric and it falls inwards, of course, that it's to be expected that at the center, you'll form some sort of singularity. So people were saying, well, okay, we have this one example, but maybe this is just because of the spherical symmetry. So we don't know if really these singularities do exist in nature, or maybe this is just an artifact of our model. And what Penrose proved was that under certain circumstances, the key ingredient in this theorem was once something called a trapped surface is formed, then for sure you'll have a singularity. So you have an argument, a mathematical argument, that tells you that if so-and-so happens, then your space-time will contain a singularity. This trapped surface, by the way, it's an interesting idea. It's a surface that's so. Let me give you the thought. So think of a sphere, and suppose that there's a flash of light along the surface of the sphere. So you have a sphere, and all of a sudden there's a bolt of light all along the surface of the sphere, and so you have a spherical wavefront propagating outwards, spherical surface of light, and one propagating inwards. The light going outwards forms an ever-expanding sphere, and one going inwards forms a sphere whose area is decreasing. So a trapped surface is a surface like the sphere I was describing, but such that both the light that's going outwards and the light that is going inwards are contracting. The areas are becoming smaller in both directions. And of course, you cannot do it here in this room, but you can do it inside a black hole. And so his idea was, well, if you have a space-time and you know that at some point you have one of these trapped surfaces, then you must be inside a black hole. And so you'll find this singularity. And this is actually a good reason to think that general relativity is not the final theory, if there is such a thing, because the theory itself predicts that you'll find these points of infinite gravitational field. So these points where it stops making sense.
Maybe can I make a remark? So actually, just to put some controversy, my understanding of the singularity theorems is that actually you have something that is called geodesic incompleteness, right? So
Yes.
there's still a gap between geodesic incompleteness and curvature singularity, and that's another example of, I guess, like this also physics and mathematics, duality, because like singularity can mean many things, and in this case, for instance, it is my understanding of the theorem is that it shows geodesic incompleteness, but that doesn't necessarily means curvature singularity, which is the thing that like we see all the time in the classical examples, spherical symmetric examples that you're describing. So actually that shows that there are still, even in those cases, like a gap for the mathematics to refine that bridge between what we expect physically and what we can prove mathematically.
Yes, typically picky mathematician. but what he's saying is completely true. Yes, what he proved was not actually that you have a singularity, it was something weaker.
Bob, I wanted to ask you about that. I suppose that you were slightly too young to be working in the field when those first theorems were proven, but I suppose that you were already active in the time when, like, in the aftermath of those theorems.
There was, so the original Penrose singularity theorem, I don't remember the exact date, but I think 1965 is about right. I started graduate school in 1968, so that result was clearly already on the table before I had any idea what general relativity was. But in the late 60s and the early 1970s, there were further developments of singularity theorems. That original Penrose singularity theorem, some of the basic ideas and the arguments, Hawking generalized that to a cosmological theorem. If you had, an expanding universe or whatever that would, and go backward in time, you could make a kind of similar argument. And then there were further generalizations by Hawking and Penrose. So those developments were occurring while I was a graduate student, and a lot of the ideas were then being applied to similar ideas to the theory of black holes. The area theorem is based on very similar arguments. And that was going on while I was a graduate student.
So do you think this was a case in which sort of the theorem came and then immediately many people were very excited about it, and then there was a lot of development right away? It wasn't that people were kind of holding back.
There wasn't some big crowd doing general relativity, and I mean, it wasn't like, the string theory community today, where there would be an idea out there, and as soon as some idea is put out, there'd be 50 papers the next day developing it, or whatever. I mean, there were only a handful of places doing anything in general relativity. Now, quasars had been discovered, several years before the Penrose singularity theorem, and that was the first Texas symposium, that was primarily raising the issue of what could these quasars be, and is gravitational, is it the gravitational energy that's involved? And if that was the case, then things would be close to gravitational collapse. So what would be going on there? So, I mean, I'm pretty sure Penrose was at that first Texas symposium and so on. I think it was, those ideas were very much in the air, and that, I think, did lead to, Penrose's thinking of these issues of gravitational collapse and under what circumstances would you have it. And I mean, just to follow up on what was said, I mean, in the spherically symmetric case, where you have a Schwarzschild metric outside and you get a Schwarzschild black hole, you have these trapped surfaces within the black hole. What Penrose showed is that all you need for the singularity, in the sense of having null geodesic incompleteness, that none of the singularity theorems say anything about what the nature of the singularity is other than geodesic incompleteness. If geodesics stop after a finite amount of time, something's wrong, but the theorems don't tell you what. But now, if you didn't have exact spherical symmetry, you can argue that you'd still get trapped surfaces. That doesn't, that just depends on the metric being not so far from the Schwarzschild metric, but it doesn't have to be exactly spherically symmetric. So that was a convincing demonstration that the spherical symmetry was not, the singularities that you get in this vague geodesic incompleteness sense was not an artifact of spherical symmetry. One thing Penrose did not show, and has not been shown, of course, is that you actually get a black hole and the singularities are contained within the black hole. I think that Penrose's Nobel Prize citation says something to that effect, but when he mentions that in talks now, he's always takes a minute to say that he didn't show anything about black holes. He just showed things about singularities.
Yes, you're right. I checked that in the preparation for this. I checked the citation on the Nobel webpage, and you're right. It does say for showing that black holes are a robust prediction of general relativity or something. But I don't know.
So anyway, to get back to the original question, I mean, I don't think so. Who is interested in theoretical physics or mathematics, even in gravitational collapse issues? Well, Penrose was fairly well. It was really quite remarkable that basically on his own he came up with these ideas that involved techniques that had not been used previously in general relativity. But, Wheeler at Princeton was very interested in gravitational collapse. He had a large number of students and so on in that area. I mean, Kip Thorne at that particular time would have been there. And of course, later, Bekenstein, Unruh, I was there, and so on. We all got very interested in black holes and collapse issues, and to some extent using these singularity theorem arguments. But otherwise, I mean, Sciama in Cambridge was, found this interesting and got Hawking interested in it. So there was work being done there. Yeah, the very important figure that I should have mentioned at Princeton is Bob Garroch, who himself, made some very significant contributions to the singularity theorems and global methods arguments. So that was kind of it. I mean, Penrose, who was in London at the time, Hawking, and Carter, others at Cambridge, and Garroch and others at Princeton. So it wasn't, so these people, put their efforts into it and came up with, remarkable further developments that took Penrose's ideas quite a bit further than Penrose had taken them. But it kind of wasn't like, if there had been archives, then it's not like the archives would have been flooded with papers in this direction.
Interesting. I wanted to ask Edgar actually about another. So this is kind of the idea of the very strong gravitational field, which Penrose did so much back already then to revolution our understanding of. But another of his ideas is about weak fields, and I wondered if Edgar, you could explain how these mathematical ideas have influenced your work.
Okay, so just to give continuity to what has been said, so Penrose was like very prolific in terms of ideas, and so besides the singularity theorems and other techniques that he introduced to the field, which actually I read some people even say that like when they started using those techniques, it sort of separated theoretical physics from mathematical physics in GR. So he really started introducing very high level techniques, exporting that from maths. And one of those techniques that he imported, for instance, in the case of the singularity theorems, a lot of topology. In the case of other of his contributions, he imported the concept of conformal compactification. So this is not something that he invented by himself, but it's something that he sort of brought to the field of general relativity. And this idea of conformal compactification is that it's a way to encode infinity. So one of the things that he was interested in is the so-called weak field. And weak field, by weak, we mean that imagine that you have a gravitational system, say a binary system, so close to where the action is happening. Well, this gravitational field is quite strong, but when you go very far away from it, so the field should decay, should become weak. But weak doesn't mean boring. Actually, from theoretical physics point of view or mathematical physics point of view, can be actually quite exciting, because then it comes tricky once you introduce the word infinity, because what is infinity, right? So it's not something that you can sort of we don't experience that in our daily lives. So you have to come up with a way to encode this weird thing which we call infinity. What do we understand by infinity? So what Penrose did was to introduce this concept of conformal compactification, which in a nutshell is the idea that you bring infinity to a finite distance, and the best way to explain this is through a joke. I don't know if you have heard it. So, and the joke is how a mathematician can trap a lion. So he goes to the jungle, he has one cage, and to trap the lion, what he does is he enters the cage and then makes an inversion. When he makes the inversion, all of the world is inside the cage and he's outside. So this same idea, which in this joke, is the same, morally speaking, the same idea that one can apply to sort of compactify the space-time and to bring it to a finite distance and try to trap that really difficult lion in a finite cage where you can really study, in this case, let's say in this analogy, the borders of the cage where this lion is sort of trapped. So that is the idea of this conformal compactification. And this was very crucial, for instance, for physics concepts such as gravitational waves. So it turns out that this very, let's say, abstract idea wasn't just playing with ideas. At the end of the day, it was crucial for the mathematical understanding of something as fundamental as gravitational waves.
Well, now that actually fits perfectly with the next question, which I wanted to ask Bob. Well, first of all, gravitational waves were detected first directly in 2015, and they marked a complete sea change in our subject. What are gravitational waves?
Well, I mean, in general relativity, well, in special relativity and maybe even pre-relativity physics, the structure of space-time can be described by a space-time metric that is basically giving you the time intervals and space intervals between events. I mean, let me not try to explain that in, with more mathematical precision or whatever. But certainly in special relativity, in pre-relativity physics, you have a metric of space and a kind of separate metric of time that's trivial. In special relativity, they're put together in a space-time metric. The big thing in general relativity is that this space-time metric becomes dynamical and is subject to equations that, at least in the weak field limit, are very similar to Maxwell's equations. So
yes, I think Margaret was showing this nice picture in her slides that showed sort of the warping, at least as a visualization of that idea.
Yeah, but now we're interested in a time-dependent situation, and we're not, for the gravitational waves, and we're interested in the matter that will act as a source, the same way as, in a similar way, the charges would act as a source for Maxwell fields. But the key point is that the deviation of the metric from flatness will satisfy a wave-like equation, much like Maxwell's equations for the electromagnetic field, that are sourced by now masses and motion of masses in the same way as Maxwell fields are sourced by charges and currents. So the idea is that if you have a strong enough source, like a binary black hole, of course, is the prime example of something that would be a source of this sort and has been observed to be a source of this sort. But you have two black holes that are very near each other and orbiting each other. They'll eventually merge, and that will briefly be an even larger source of radiation. But even just while they're merging, while they're orbiting each other, I should say, much like if you had two charges orbiting each other in Maxwell theory, you're going to get radiation. In this case, the radiation that we're talking about is gravitational radiation. And, that, is something that, as LIGO showed, can be and has been detected. So these dynamical disturbances of the metric from flatness, is something that has now been observed, and that's that was what.
And so far, right, and so far, all of those observations, they seem to sort of give yet more evidence that GR is correct, right? So my next question is, given all of those successes now, going back to all of the way to 1915, if one wanted to be very kind of provocative about it, I'd ask, isn't there a case to be made now that GR is the final answer when it comes to gravity? Jose, I can see him smiling a little bit because he already gave us one of the reasons why it can't be. But my question is, if GR isn't the final answer, then why not?
Well,
this one's for Bob, and then Margaret come in after.
Okay. Well, so, in some sense, I mean, I would say, at the classical level, Maxwell theory is the final answer on electromagnetism. But of course, it's not really the final answer. There's quantum electrodynamics, and then electromagnetism is really part of the electroweak interaction and all that. So, but it's not like Maxwell's equations are wrong at the classical level. That is what you will get for the theory, and we don't have to sort of look around for some correction term that, cubic in the electric field that we need to add to one of Maxwell's equations, to get the correct theory. I mean, Maxwell was at the classical level, at the level that Maxwell would have intended. Of course.
But then, do you feel
anything beyond that at that point? But so, at that level, I'm certainly convinced. Of course, this is a subjective judgment. So, but I was already convinced before LIGO. I mean, evidence for gravitational radiation, convincing evidence from, binary neutron star, the, decay of the orbits of binary neutron stars. I mean, that was already very convincing for gravitational radiation, given that the waveforms that LIGO is observing are completely compatible with what you'd expect from black holes. That doesn't rule out that there could be other corrections or there could be other, but I'm certainly convinced that general relativity is the final answer to gravity in the same sense as Maxwell's equations are the final answer to electromagnetism. But of course, they're not the final answer. Gravity clearly needs to have a quantum version of it. I mean, that might be the quantum theory of gravity might be very different from the quantum theory of electromagnetism. We don't know, but it can't be the final answer.
Thank you. I love that answer because you're saying all of my own prejudice back to me.
Okay.
So thank you. Margaret, you wanted to come in.
Yes, I'm not at all an expert on the theory of general relativity or on alternative theories, but I just wanted to comment that there's a lot of activity on alternative theories.
That's true.
Testing them on large scales in the universe. And one of the reasons for this is the existence of dark matter and, even worse, dark energy, neither of which anybody can understand. And as I mentioned, dark matter has been around with us for 90 years, and we don't know what it is. And the universe offers some tests on very large scales, and one of those tests come back to gravitational lensing. So on very large scales, you have two different tracers. You have a relativistic tracer, which is the light that propagates from these distant sources. And you also have a dynamical tracer that you can compare with. And so people point out that on various scales in the universe, you can make direct tests of general relativity, and there's a fair amount of activity in that. So far, there are a lot of different theories, and so far the observations have not reached the level where they can really discriminate among these tests, but I suspect they will.
Thank you. That's a very interesting piece of sort of input.
I just want to add, just to jump in, sorry. My remarks that I am convinced that general relativity is, quote, the final answer, as in the sense that I meant it, does not mean that I think people should stop work on alternative theories or should stop work on testing general relativity.
I understood that, of course.
I wasn't. Absolutely, no.
I also understood that, and
I just wanted to make sure that my comments wouldn't be misinterpreted as saying, I'm not interested in anyone who says they're working on alternative theories or whatever. I mean, I think that it is important to keep probing.
Yeah, and then so your feeling in the case of dark matter and dark energy is that somehow it has to be something external. It shouldn't be viewed as a modification of gravity.
You're asking me. Sorry, was that a question addressed?
Yes, no, it was addressed to you again, Bob. I'm sorry, I don't know. Maybe my internet is.
No. I mean, I think plausibly. I think the most plausible thing is that dark matter is some kind of ordinary matter. I mean, obviously not part of the current standard model, but and some other obviously matter that interacts very weakly with the matter that we are familiar with, if at all, other than gravitationally. But that, it's a huge issue and question of what is it, and an urgent question, and that's being pursued on many fronts. But I don't see any reason now to think that it isn't ordinary matter as opposed to a modification of gravity. And dark energy seems to be a cosmological constant. It's weird that we have a cosmological constant with this strange value. So that's certainly something to think about and worry about. But again, I think the modification of general relativity that Einstein made in 1917 is adequate to accommodate, what we call dark energy.
Margaret, you wanted to come in again?
Yeah, I just wanted to tell the story just as a counterpoint and as kind of a warning to all of us. I just wanted to tell the story of the discovery of Neptune. Now, what happened with Neptune is that people observed irregularities in the orbit of Uranus. Some people proposed that there was something wrong with Newtonian gravity. Others said there must be another planet out there. They predicted where the planet was, and sure enough, there was another planet out there. So I think it's just it's a warning. The thing that's strange about dark matter is that the parameter space for these particles is getting smaller and smaller. And the question, one of the questions I always ask is, when are we going to give it up and realize something is wrong?
Well, maybe people do realize. I know
that's sort of a heretical view, but it's very rare that you have a problem around this long in the physical sciences without a solution. So I think it's something we're thinking about, especially for young people. What is it? And it's worth I don't want to say having an open mind, because I don't want to imply you have a mind like a sieve, but it's worth thinking about what could be wrong, if anything.
But do you think that maybe this is also part of that general trend in physics, that now the kind of the length of time we have to wait between an idea and then testing it experimentally has become so long, because experiments are getting bigger and more expensive. So maybe that's part of the explanation, right? It's just become sort of cost.
Well, we have lots of experiments.
Yeah. Okay. Yeah. No,
so
point taken.
I mean, it's not that we don't know.
This isn't. You're saying
this
a case of that. Yeah. Okay. Okay.
This
good.
is not a case of that, and you know, there. I think, you know, it is worth thinking about what's going on these large scales that we can't really access. So I think one has to be, you know, ask the question.
Yeah, I don't think you'll find any arguments about that. Well, I hope not. Edgar, I saw you raising your physical hand, not your Zoom hand.
I wanted to ask Margaret and Robert and also Jose. So I've heard this same story of Neptune in astronomy, and also, but there's also the counterpart of Mercury, right? So in the case of Neptune, it's not that there was another body there disturbing the orbit, and also, but in the case of Mercury, in the case of, in one case, what my question is, in the case of Mercury, it was general relativity that was like gave this correction. In the case of Neptune, well, it was. So what I'm saying is both Neptune and Mercury at the moment was like dark matter, and in one case it was a physical body that was there, and the other case it was the theory that had to change from Newton to GR.
Yeah, so that's a very astute observation.
Yes.
So I think within astronomy you can find both examples, right, of those anecdotes. So my question is, to your point of view, is dark matter and dark energy more like Neptune or more like Mercury?
Toss a coin.
It's hard to say, because of course after Neptune there was Pluto. It took a lot longer to find Pluto. I mean, the same argument came up again. There ended up being Pluto, and even now there's the issue. If you look outside the solar system, in the outer regions of the solar system, there is a system of bodies called the Kuiper Belt. And the reason the Pluto was demoted is that it is similar to the objects in the Kuiper Belt. But the weird thing about the Kuiper Belt is that the objects in the Kuiper Belt have two kinds of orbits, and people say there must be a perturber, planet X, and nobody's been able to find it.
Yeah, that's interesting too. Bob, in part of the answer you gave to the previous sort of big question that I asked, you said, you know, GR, you believe it to be the sort of the final answer when it comes to classical gravity, but it's not the final answer because of quantum gravity. And so that leads me to another question that I have for you, which is, I notice on your webpage, when you write that you work on quantum gravity, you don't say that you work on quantum gravity. You're very careful in the way that you word that. I think you say something like you work on quantum effects related to gravity, something like that. So my question is, why do you use that terminology, and why do you not, you know, sort of jump in, given that you work in the place where loop quantum gravity was invented, right, at least to some extent? My question is, why did you never make the jump into working in full quantum gravity?
Well, for just a small, I mean, let's say Abbe Ashtekar was a student at Chicago, but he didn't develop gravity until he left.
Okay,
he was a student at Chicago prior to my arrival as well. So, I mean, thank you. That's not the point of your question. So, well, I said in the beginning that, you know, probably a bit over half, I mean, 2/3 of my work is probably I would estimate is in classical general relativity, and most of the rest is in quantum field theory and curved space-time, or in fact, recently I've done a lot of work that are kind of considering quantum superpositions of massive bodies and issues that arise in that kind of case, so that there has to be some quantum gravity associated with that and so on. So, but the reason is I don't have any good ideas for how to formulate quantum gravity. I would certainly work in that area if I had some good ideas. So the formulation of how quantum fields behave when you have a curve as opposed to flat background space-time. So, quantum field theory, as you'll find it in quantum field theory texts, is of course in the context of special relativity with a flat background metric. There's a lot that changes if you have a curved metric, and particularly a curved dynamical metric. You don't have a preferred vacuum state. A lot of the tools or other ideas that play a central role in the usual formulation of quantum field theory are not present. But there's a completely well-defined way of formulating quantum field theory in curved space-time. That's something I've been very interested in and did a lot of work on, particularly 15 to 20 years ago with Stefan Hollins. So that's been a significant component of my work. And of course, the Hawking effect and things related to that. But I don't have any good ideas as to how to formulate quantum gravity.
So is the hope
papers on that and all that, but that's about it. So it's not very much of the body of my work.
Maybe sort of this goes back to the part of the earlier discussion, right? When sort of the question of mathematics versus physics. I suppose if you make a completely self-consistent formulation of quantum field theory in curved spacetime, maybe that gives you a sort of a hint in how to go beyond that in the absence of having experiments to tell you what to do.
Well, that is certainly part of my motivation in working in the subject, because you really have to change things in the formulation as compared to how things are usually formulated. I mean, again, where some preferred vacuum state, plays a central role in what you'll find in quantum field theory texts, but what you'll also find in, in Whiteman axioms and things like that. I mean, so to get away from that and see what the key ingredients are, it's certainly my hope that'll give some clues as to what to do in quantum gravity. I mean, that's a definite motivation.
But you're saying that sort of so far along that road, even though now there's the sort of the self-consistent formulation, it didn't quite give you the insight you wanted.
No, I mean, because the kind of causal structure given by a classical background metric is still playing a very central role, and that's the fundamental thing you'd have to give up, presumably, in quantum gravity, where the metric is now, in general relativity, as I previously said, it's a dynamical variable. It's the thing that will be quantized, so to speak. So it won't have a definite value. So presumably two events might be causally related or might be not causally related. What do you do then? That's related to other problems of, there isn't, the quantum field theory in curved space-time is still formulated in terms of defining local observables, the quantum fields being the local observables. But when you are trying to, when you've got diffeomorphisms, coordinate transformations or moving points around in space-time as your gauge transformations now, then it isn't even clear what you mean by a local observable. So, so the ideas of quantum field theory and curved space-time that really do work beautifully to formulate the theory of quantum fields in a classical curved space-time don't really get off the ground yet. It's not like they sort of just don't quite make it. I'd say they're not even close to give it at the moment, at least to giving the concepts and tools that I would expect would be needed for quantum gravity. But again, dropping the preferred vacuum state and so on is probably
also needed. Yeah.
Direction. Yeah.
Yeah. Thank you for that. That was a great answer. I've got one more for you, Bob, and then sort of a cheeky one after. The one more, the real one, is that your book, your textbook in General Relativity is rightfully seen as a masterpiece. And the question is, if you were writing it today, are there any additional topics that you would cover that you didn't cover in the version that exists?
I say, okay, that was a question I wasn't especially anticipating. I mean, I've not, written a second edition of the book. I mean, basically because there isn't that much at a conceptual level that really needs updating, and it would then be an awful lot of work to do. I mean, there are definitely things I would do differently. Now, the cosmology section is very badly out of date. There's been a lot that's happened in cosmology, but the FLRW solutions are still solutions, and all. So even most of the cosmology chapter is absolutely fine. I wouldn't change that. The stuff that relates with observations and what our universe is like and so on, I would definitely want to update that. But that's probably the only. So the section of the chapter on cosmology where I relate with observation. I mean, there's a lot of Big Bang mention, brief discussions of Big Bang nucleosynthesis. I mean, that's pretty much fine, but there's, a lot has happened since 1984 with the cosmic microwave background and what we've learned from that. I mean, there's some discussion of that in there, but not up to date by any means. Anyway, I don't have to belabor that, but there's not that much else that that would really need update. Now, I mean, the quantum gravity section surely would need to be rewritten to kind of summarize with more modern ideas, but that would only be providing some superficial summary anyway, and all that. I mean, it's not. I wouldn't have.
It's nothing foundational, certainly.
Yeah, well, I wouldn't have. Yeah, I mean, the issues are still the same, and most of that chapter is on quantum field theory and curved space-time. That could be updated, but so yeah, I mean, I mean, when my views on the importance of certain topics, like Lagrangians and so on. I mean, I think they're really much more useful and important than I did when I was writing the text. And so, I mean, I'd make there are a lot of small changes. I wouldn't stick the Lagrangian and Hamiltonian stuff in an appendix. It would make it into a full-fledged chapter. But really, I'm not at all driven to write another edition. And, I think the benefit ratio would be very high. The cost to me versus the benefit of having the new edition would be a very high ratio.
Well, then my cheeky question is that I saw that you've recently written a book about advanced electromagnetism.
Yes.
So now you've got general relativity and electromagnetism. Are you planning on writing 2 more?
Well, I would. It would be if I, had another 20 years and a lot of active life and a lot of free time to do it, I would definitely consider writing a quantum field theory book. But I don't think that's going to happen.
I certainly would.
The electromagnetism book just happened because I was teaching the course again after not having taught it for 20 years, and I really got completely fed up with how electromagnetism is being presented. I mean, the kind of quasi-historical Coulomb's law, and you introduce an electric field and you introduce potential. I don't know. I can go into that. So I kind of taught it really, mentioning all the basic ideas that I thought were fundamentally wrong in the way it was presented. And then I found it was really fun to teach a standard course the rest of the way, where I don't have to kind of, make compromises in the way I'm describing things or whatever, because, we're not going to introduce the potentials until later, or
so that you could go and do it really your own way from the beginning.
Yeah. And then, and after teaching it once or twice, I decided to write up lecture notes. And then when the pandemic hit, I figured I might as well take the time to make it into a real textbook. I mean, most of the lecture notes had been written up then.
Yeah, time well spent. I wanted to ask all of you now the following question. So as you see it, how do scientific controversies in your fields actually get resolved? And here I wanted to ask you also, have any of you yourselves been either sort of a strong opponent or strongly in favor of a certain idea or concept, and then come around to being a true believer, or have you been deconverted? So that's a big change from the previous. Or have you always settled on like when you formed your opinion the first time round, if you formed a strong opinion, did you then always keep that strong opinion? Do you hear me?
Yeah, we can hear you.
It means that. So here for the audience, it means that. Margaret, go ahead.
I can say something about that, about the original discovery of the cosmic web. So when I began to think about the distribution of galaxies in the universe, people actually thought there weren't any large-scale patterns, that there were clusters of galaxies like the Coma cluster I showed, and that they were randomly sprinkled in a sea of other galaxies. And at the time, my colleague John Hucker and I and our student Valerie Lebrun had access to a captive 60-inch telescope on Mount Hopkins, Arizona, which was just big enough to map the distribution of galaxies in the nearby universe. And it occurred to me that, of course, the universe is big and life is short. So it occurred to me that if we mapped galaxies in a slice of the universe that was deep enough and wide enough, we would see whether there were any large-scale coherent patterns and how big they might be. And by analogy, let me just say, if you approach the Earth and you could only map a small fraction of it, what kind of sample would you take? Well, if you take a patch, you're not going to learn anything. Mostly they land in the ocean. But if you take a great circle in almost any orientation around the Earth, it will cross continents and oceans, and you'll find structures that are both big. So with that analogy, we mapped a slice of the universe, something that went across the sky as far as it could, and the thickness is set by the density of galaxies and so on. And the amazing thing is there was a pattern nobody could deny.
And so they didn't deny it anymore.
There was debate about how general it was, and it turns out to be very general. That pattern in the first slice is the pattern you see throughout the universe. And I mean, if we have time, I can show you not the pattern in the first slice, but what the pattern looks like as you go deeper into the universe, what it looks like as you map the universe. I don't know if we have time because you'd like to give people a chance.
Yeah, we're now running quite short, but I wanted to ask you there. So when you entered into doing that work, did you do it kind of with a completely agnostic point of view, or did you yourself already think that there was structure and you were going to sort of show everybody, or did you just think, well,
I was educated where everybody knew what the structure was. There wasn't any.
Oh, I see. So this is
and so neither John Huckra nor I thought that there was any structure. But let me show you a deep let's see. I can just show you.
Yeah. Go ahead.
Why don't I just show you? I'll share my screen and I'll play a movie and somebody else can talk over it, because I'll just play a movie that shows what it looks like when we map the universe. Oh, why is it doing this? Just a second. Okay, so this is a movie of the way we map the universe. And so the way it works is we sit here on the Earth and we look out into the universe, and the galaxies here have an age of 8 billion years, and the universe now has 14 billion years. And each point that you'll see represents a galaxy. And what you'll see is that they make a kind of web-like pattern. So as it goes, you'll see the observations. So we observe with a telescope, and each field will show. So here you go. And now you can see this web-like pattern with very dense regions that contain clusters like the Coma cluster, and these huge holes that are called voids. And this is the characteristic structure of the universe that really showed up very cleanly in our first slice. And I can play that again while somebody else talks about their experience.
Does anybody else have an experience of that type? I suppose here that the question is maybe not so much one of surprises, but rather where you like changed your mind, right? Okay, well, if nobody had the joy of being deconverted or converted, then let me move on. Thank you, Margaret. So I wanted to ask José a question aimed kind of at, well, for the low audience locally, which is how has the study of general relativity developed here in Portugal? And well, then as following on for that, do you recommend that young people here enter the field? It will be yes. You say no.
I mean, I for anyone who's interested, I think it's a wonderful subject. It's at the crossroads of many subjects, so you can approach it from the more mathematical side, as I do, or well, you have here examples of people who were working on relativity from different angles. So in Portugal, actually, there is some tradition. Actually, there was a professor here at Técnico who used to correspond with Einstein, and he taught the first relativity course in the 20s, I think. So there was some, but that was lost somewhere when he retired. But more recently, there have been many people studying relativity. There's a very strong relativity group here at Técnico, to which your moderator belongs, actually. So anyone who wants to study relativity in Portugal has a not only here but mostly here, I would say, has a very good place to learn, and it's a wonderful subject. Can be approached from many angles, and moreover, I mean, there's a wealth of data coming in from gravitational waves and from cosmology. If you look at the Nobel Prizes that have been awarded in the last 20 years, there's an amazing amount of them have been awarded to people working on relativity or thereabouts. Like there was a Nobel Prize for black holes, there was one for gravitational waves, there was one for the structure of the early universe. So it's sort of a hot subject at the moment, although it's 100 years old. It's still producing Nobel Prizes. So yes, definitely, I would advise anyone who's interested to go into the field.
Oh, thank you. A strong, if predictable answer. Thank you. I wanted to ask another one. So this one's primarily aimed at Edgar, because I think he's the one of us who, well, you're still in the career stage where this potentially applies. So one of the questions from the participants was, when you study or work abroad, what is the process of getting used to another country and its language like? This isn't really a relativity question, but it is one that's certainly very relevant to young people thinking of going into the world of science.
Well, first of all, I'll say that I mean, independently of if you're doing science or any other human activity, like going abroad, being exposed to, I don't know if this word exists in English, the otherhood, so other people's way of thinking, other people's way of speaking, other people's way of life, actually at the end of the day enriches your own life and broadens your perspective. And actually that would have even an impact in science, because in science, like if you are working in a certain field and then you interact with other people from other fields, you might learn something from the techniques of the other people in the other area that might actually help you in your own area. So I think this cross fertilization happens in science and also happens outside of science. And sometimes science drives you to actually have this cross fertilization, not only on science things, but you go abroad, you are confronted to other cultures, and I think that ends up enriching your life.
Thanks, Edgar. I wanted to end with a question. Now we're running quite short of time, but I wanted to end with a question to both Bob and Margaret. And the question is this: throughout your careers, you must, of course, both have come across a multitude of talented researchers and scientists. Which of those have influenced you the most, and why? And I don't mind who goes first. Maybe Margaret, you should start, and then Bob, you could go after.
Well, I guess in my case, it's a hard thing to answer, but probably the person who influenced me the most was Vera Rubin. And I think it's because she was the first really distinguished woman I met who I could admire. When I was a student, I did not have a single female professor throughout my career. And
truly
zero.
none.
Zero. And when I met Vera, which was early in my career, it made a huge difference to me to be able to talk to someone who had also lived it and who had also really made a mark in science. And she was a remarkable person. And both my husband and I stayed with her and her husband in her home and so on. And so I had not only a wonderful collegial relationship with her, but also I admired her as a person, which is very important to me.
Thank you. A beautiful answer. Bob?
Well, I mean, in terms of influence, as already mentioned, I mean, the Penrose, and while I was in graduate school, I mean, the Hawking papers were being written, and, you know, the Hawking particle creation paper, which, you know, was an absolutely incredible paper in many respects. I mean, they certainly had a tremendous influence on, you know, not at a personal level, but at a scientific level of, you know, what kind of science do I want to do, and how do I want to do it, and what kind of standard should I apply? I mean, that certainly shaped, you know, their work and writings certainly shaped my early career at a more personal level, but also, you know, at a scientific level. I mean, I think there's no question the person who had by far the most influence on me was Bob Garroch, who, well, I had actually interacted with him. I mean, corresponded with him a lot even before I came to Chicago. But once I arrived at Chicago, I mean, particularly my first couple of years here when I came as a postdoc, I mean, I spent more time in his office than mine, and the whole freewheeling style of, you know, you kind of think everything through by yourself. You don't kind of rely on any authority, and, you know, or accepted knowledge or whatever. It's just, you know, is this really true, and how do you prove it? And, you know, that kind of way of thinking, and bringing in a lot of ideas to play. I mean, ideas that might even seem to be unrelated, but you kind of bring them in and see if they are or aren't, and so on. So, I mean, that had definitely an enormous effect on, you know, the way I did physics, the kind of, you know, standards that I applied, and, you know, well, to some degree, some of the problems that I'd be interested in working on, although I think that was probably more set earlier. I mean, I was interested in black holes for sure and all that, but that certainly had a big influence on, you know, my career and the way I do physics.
Thank you. I can see now that we're really running short of time. So I think all that's left for me to do is, first of all, I want to apologize to those students in the audience to whose question I didn't get to, but I hope that you'll agree that this was a huge amount of fun. I've certainly learned a lot, and I also really enjoyed the interaction between all of the speakers. So I want to thank Bob and Margaret and Edgar and José again for giving us their time so generously. And I think that's it from us. João, Vasco, do you have any closing remarks to make?
Can you hear me?
Yes.
Yeah.
No, I
Okay,
I do hear you. Yes.
Okay. Okay. Yeah.
Perhaps you can step in front of the audience so that we can see you if you have the radio
Okay.
mic.
Can you see me and Vasco here?
We see you both, yes.
Yeah, okay. So I think this went well. Probably after the roundtable, I think Edgar and Jose, you can speak to them a little bit if you can. But so I would like to thank you, all of you, for having been here. Having this discussion with some brief moments of possible tension, which were really cool. But yeah, so I really thank you for having been here, and I would like to pass Vasco.
Yeah, I also think this was an amazing opportunity for the students and everyone that is here or in Zoom and on YouTube. And maybe if the students have some question, they're free to ask. We can pass the mic. No? Okay. Yeah. We should also thank the moderator that actually kept everything running smoothly. So
Okay.
thanks, David.
Thank you.
This question is kind of like 2 in 1. So I would like to ask, how does chaos affect our understanding of the universe and the cosmos? And well, if we tamed chaos, how would we use it? And what would happen? Oh, sorry. Yes. Okay.
Well, maybe I can answer that. So chaos is a technical term. It means essentially sensitive dependence on initial conditions, and so essentially what people have learned is that once systems get sufficiently complicated, this chaos usually turns up. So what happens is that it's very hard to predict what's going to. I mean, you can do it in theory, but in practice, it's very hard to predict what's going to happen. So that means that in certain situations, like for instance, the weather is like but it also happens in relativity, by the way. But the weather is the example that everyone gives. It's very hard to predict the weather after a certain number of days, simply because if you change your initial conditions a little bit, the weather will, after 3 days, 4 days, will change completely. And it's impossible to know exactly what the weather is now, because you cannot measure with infinite precision. So that's what chaos is. And it does not affect. It affects our ability to predict what's going to happen. And I mean, you cannot tame chaos, because I mean, what would you do? It exists, and you have this limitation. So but it's a good point that chaos is stopping people from doing certain things. For instance, a very good example is nuclear fusion. If you want to understand the plasma inside a nuclear fusion reactor, chaos turns up, and it's really, really hard to make the plasma stay inside the container. So in that sense, it's you would like to tame chaos, but
Okay, thank you.
Any more questions? Okay.
Before that, I should say that I really am going to have to leave within a few minutes, because I had, made an appointment on the assumption that
yes,
that's by about now. So
that's quite
I can
okay.
perhaps stay for another question, but I will have to leave shortly after that.
I think maybe we should make this the last question.
Hello. I would like to ask you about mass and energy. As Einstein said, like a little amount of mass can transform into a big amount of energy. So what would you consider as the boundary between mass and energy, since light is energy and light is made of photons? Thank you.
I'm not sure the question was about relationship between mass and energy.
Yes.
I mean, in general relativity theory, they are the same thing. I mean, so, energy can take various forms, including ordinary matter or photons or, electromagnetic energy. And of course, they can be converted into each other. So, a ball of electromagnetic radiation will have mass. It will gravitationally attract in much the same way as some, ball of ordinary matter would. Of course, the electromagnetic radiation will disperse out if it's, reasonably weak field and isn't going to so dense that it isn't going to collapse into a black hole. I mean, but the mass and energy, I mean, they are the same thing, as I already said in general relativity. So there isn't really a distinction. There's just a distinction between, different forms of energy that the energy will take. So I'm not sure if that answered the question, but
I think it answered.
Thank you. Okay, I think that we should stop here. Thanks once again to everybody for being there, to the audience, to Bob, Margaret, Edgar, and José, and finally, thank you to the organizers for setting this up and setting up all of the cameras and all of the technology and all of that. It's been great. See you again.
Okay.
Bye, everyone.
Bye-bye. Thank you.
Goodbye.
I can run down and say hi to everyone. I'll be with you very shortly.